Hello students, welcome back. Previously, we went through the definition of the Laplace transform, Laplace inversion, and a bunch of examples, starting from the motivating examples and then the real examples. Okay, we spent quite a bit of time going through examples. However, we hardly spent any time proving anything, as a matter of fact, even though we had to use those Laplace transformation formulas for all those example problems. That's a glaring hole that we'll have to fill in. Okay, let's begin. Here's a reminder. This is the definition of the Laplace transform. Let's copy and paste this thing down here. The first property, the Laplace transform is one-to-one, so that it is invertible and we can consider Laplace inversion. But that's too hard. We are not going to do it here. Maybe in real analysis too, definitely not here. Next, linearity. This is one of the rare formula that we actually went through and proved already. I think we did it in the second video, I guess. Everybody should be able to do the first one here, the forward direction. This one is a bit harder. Technically not too bad, but theoretically, conceptually, it's a bit tricky. So the kind of student who went through the linear algebra already, they can handle it, but in general, maybe not. So only the first one is required. Input derivative rules. We went through this, yes, but let's do this again. This is so important that I'd like to do this again. How do you prove the first formula here? All I have to do is to take the integration by parts. Let's see. This is the definition, right? And then in place of y, I'm putting in y prime here. So y prime goes here, and y prime goes over there. And then we're going to be using the integration by parts. How does that work? Here's the integration by parts formula, my favorite form, minus Okay, it goes like this. U v prime dt, u v u prime v dt, like this. And what is u here? We take the exponential function. And then what is v? V prime is y prime. U prime is therefore minus s e to the negative s, and v is equal to y. Now this is one of the rare exceptions that exponential is becoming u. In calculus 2, we never had this kind of example, I think. I have never seen an example in calculus level that exponential becomes u. I mean, log function always becomes u. Exponential function always becomes v prime. That was calculus 2 rule, but here things are a bit different. We already have y prime, so it's more natural to get v prime as y prime so that v is equal to y. And then upon taking the derivative, you get negative s coming out by chain rule, and we have the exponential. So put it into this integration by parts formula, we get the second line. And then plug in the top and plug in the bottom, subtract one from the other. Plug in infinity, what do you get? E to the negative infinity, that's 0. Plug in 0, then e to the 0 power is 1. So we have 1 minus y of 0. And that'll give me this part. How about this one? Well, s is constant, and I can take it out. Minus minus plus, so we have plus and s. And what's left? It's just a Laplace transformation. So we get the Laplace transform of y. So we have capital Y there. S capital Y minus y of 0. Sorry, wrong key. We already did it in previous video, but I thought it was important enough to repeat it. Now, how do you go about the second formula and others? One way is to do this integration by parts twice, thrice, and so on. But here I decided to do a little bit more clever way. Use the first formula using y double prime. Instead of y prime, you put y double prime in there. Then you're going to get the Laplace transform of y prime here. And then instead of y of 0, I'm going to get y prime of 0 because I started from y double prime. And then how about this one? By the first formula again, we have s capital Y minus y of 0. So upon simplification, we get this. Repeat this again, and then we're going to get the third line and so on. But this form, this one is a little bit more elegant and it's more readily expanded over inductively. And if you're familiar with mathematical induction and if you'd like to get really complete, elegant solution, go ahead and do that. The detail is left to the students. Okay, input derivative rules, we are done. Next topic, translation principle, and let me copy and paste it over here. How do you prove this one? Well, e to the at power is multiplied to a certain function. It appears already in the original function. But then again, we have another exponential here in the definition. So from this definition, we have this blue exponential, and then this one came from the original. So we have two exponentials, same base, so we can combine them, and this is what we get using the exponent rule. So what do we have? Compare this with the definition, what we get? Exactly the same except s versus s minus a. So this expression must be the Laplace transform of y of t, except instead of s, we have to get s minus a. So instead of capital Y of s, we get capital Y of s minus a. It's a translation. The proof is simple, but it's useful, so please remember this. Next, dilation principle. Maybe not as important as the former one, but let's talk about it anyway. Let's see, do I really have to copy and paste it over here? I don't know. Maybe it's not really necessary, so let's just keep it hidden for a while. How do we work it out? Well, put it into the definition, except we have ct in place of t there, because we have this. That's what I have over here. We have ct. Now, let's use the integration by substitution. Let's take this to another character, tau. That's what I did. Tau is equal to ct, so d tau is c dt. Therefore, dt is 1 over c dt. 1 over ct tau, excuse me. So this one replaces dt and became that. And that 1 over c contributes to this one in the final formula. So that resolves one of the two. So 1 over c, I got it. How about the other variation here, s over c? Let's look at this carefully, e to the negative st, especially look at the power only because base is the same. So we have negative s times t. Let me expand the font even further. But t is the same as what? tau over c, isn't it? And that can be rewritten as s over c times tau, like this. So I'm basically slipping this denominator to the other number. So what did you get? Instead of s, we ended up with s over c. Otherwise the same. So what am I going to get in the end? Capital Y of s over c in place of just s. This 1 over c was counted before. It came from here. The other, s over c, came from this business. So that's the proof. Output derivative rules, I don't know whether they're going to be useful. The proofs are not too bad. I'll probably end up writing these as homework problems. Now, do we have enough time to prove some of these? Some of those I can. Okay, all right. How about the first one? It's easy. All you have to do is plug in y equals 1 here in the definition. And then what we get? We have the definite integral. So all we have to do is to take the antiderivative of this exponential, plug in the top and the bottom, subtract one from the other. And if you plug in the top, then we have e to the negative infinity, which will go down to 0. So everything makes sense. Here's the computation. Easy. Antiderivative, plug in the top, plug in the bottom, subtract one from the other. That's it. E to the negative infinity is 0. In the end, what do you get? We have 1 over s. Next problem. Okay, this one is going to be worthy of our time. If we have enough of it. I guess so. Let's talk about it. This one will require integration by parts because over here I'm replacing t to the nth power. And then if you have polynomial times exponential, that's typically integration by power. And then if you use integration by part, where v prime is exponential and u is the polynomial part, each time I take the derivative, power of the polynomial drops. So nth power will drop down to n minus first power, and then drop down to n minus second power, and then n minus third power. Eventually, the polynomial part will disappear. And each time I take the integration by part, we're taking the derivative, so we have multiplication by n, and then n minus 1, and then n minus 2. Looks like we're getting that n factorial there, so it makes sense. Okay, let's go to the proof. Let's begin with the definition. Let's put t to the nth power into the definition of the Laplace transform, and then we get this improper integral. And then integration by parts. What am I doing here? u is t to the nth power. V prime is e to the negative st. U prime is therefore n t to the n minus first power. And v is 1 over negative 1 over s e to the negative st. Check. Take the derivative, and by chain rule, we have to multiply negative s, and that'll cancel this one out, and you're going to get this one. Yes, indeed. From here, take the derivative, you're going to get that. Okay, that's simple. We have it, so let's put everything into the integration by parts formula. this is equal to u times v minus integral u prime v dt. That's the integration by parts formula, isn't it? Let's put those in. So u times v, that's what we have over here, down here. And then u prime v, that's what we have over here. First, please note that these two negatives will cancel each other out and we are going to get positive. So you don't really have to worry too much about negative signs flying around. Next, look at this part. That'll go down to 0. Why? Plug in infinity, you have e to the negative infinity. That's going to be much smaller, or that's going down to 0 much faster than any of the polynomial growing up to infinity. As a matter of fact, you can prove it using L'Hopital's rule. T to the nth power over exponential. And that's what I'm talking about. Limit and t is going to infinity and t to the nth power over e to the s times t power, where s is positive. And this is always 0 because if you take L'Hopital's rule and keep calculating the derivative of the numerator, you're going to get n minus first power, n minus second power. The power will drop down to eventually 0, to constant. If you look at the denominator, that will stay exponential. So exponential never goes away, and then eventually in the end we're going to get 1 over infinity. That's going to go down to 0. So plugging the top, this whole thing is 0 because of this. Plugging the bottom, then 0 to the nth power, that 2 is becoming 0. Either way, this whole thing will drop down to 0. And then we already talked about minus minus becoming positive. Now here, we took the derivative, so we have n just fractionally multiplied. And then from the antiderivative, we got s over here. You see this n, which I'm just highlighting in blue, and this s, which I just highlighted in red. And that's what these are. And then put those together. Let me use green this time. So we have n over s came from the integration by part. And then in the end, what did you get? We get the Laplace transform of t to the n minus first power. Let's do it again. Integration by parts, uv, and by the same reason, this will go down to 0. And then by the same reason, we have minus minus plus. And by the same reason, I got this 1 over s coming from this antidifferentiation. And then we got n minus 1, which comes from the differentiation. This one basically. So what we have, n over s was there before. Fresh new n minus 1 over s. And then we have the Laplace transform of n minus second power. Repeat, repeat, repeat. What do we get? Finally, we get n factorial over s to the nth power. And what's left is 0 power, which is basically this one. So we have another 1 over s coming from the Laplace transform of just 1. In the end, what do we get? N factorial over s to the n plus first power. So where did you get n factorial and s to the nth power? They came from the integration by part, n applications of integration by part. And we have one more s, and that came from the previous formula. That completes the proof. By the way, second proof is a little bit more elegant, but a little bit harder to understand. If you want to use mathematical induction completely, go to the second form.